Okay, let's go for the next topic. The next topic is the magnetic torque. The symbol is tau and is defined in this way. Imagine that we have an object that rotates, or it's like a rotation. When we apply a force in this direction, imagine, of course, this force doesn't produce any rotation. Now, if we change the direction of the force, imagine in this way. Now that's the force, and this force is applied at some distance from the axis of rotation. This distance is r, correct? And we have an angle theta. Well, we can break this vector into components. One component perpendicular to r and one component parallel to r. Correct? This is parallel and this is perpendicular to r. We found that this force, this component, doesn't produce any rotation, any torque, but this one, this component, right? Now, how are these three quantities related? The angle, the force, and the lever arm? Well, in this way, torque is equals to force r sine theta, right? This is the magnitude. As a vector, it's gonna be force r sine theta in that direction. That means the normal to the plane formed by r and the force. This is the plane, so normal is gonna be in this way. So that's the direction for the torque, tau. Okay, this is one convention. Another convention is this one. Imagine that we have an object, a disk, correct? And this is the radius, correct? And if we apply a force in this direction, imagine that the force is equals to 20 newtons, and in this direction, force is equals to 10 newtons. The convention now is this one. If the rotation is counterclockwise, the rotation is positive. If it's clockwise, it's gonna be negative. That's another convention for rotation. Now, let's find the net torque for this case. So the net torque is equals to okay, as a vector, torque 1 produced by force 1, this is force 2 for instance, correct, plus torque 2 produced by force 2. Remember, these are vectors. Now let's do it. What is the magnitude for tau 1? Torque 1 is going to be force 1 r1 sine theta 1. Direction clockwise, positive. The next one, what is the magnitude? F2 r2 sine theta 2. Direction clockwise, negative, minus. Perfect. Now, what is the angle? The angle is this angle, right? 90 degrees for both cases. So sine 90 is 1. Great. So what do we have then? And this r is going to be the radius and the radius. Imagine that the radius is equals to, let's say, 20 centimeters. An example. Okay, let's do it. So what do we have then? This is gonna be 20 newtons times what is r? It's gonna be 0.20 meters, correct? Minus what is F2? Magnitude 10 newtons. 10 newtons times r2. What is the same radius? It's gonna be 0.20 meters. And we get then that the answer is gonna be 4 newtons meters minus 2, right? Newtons meters. Correct. And then what is equals to 2 newtons times meters. And it's gonna be the net torque. Okay, now let's apply these ideas to a magnetic torque. When we have current through a wire. Okay, now the wire is represented by this segment, and we have a force acting on the wire, the magnetic force. Okay, let's do it. Imagine that we have a conductor, right? A conductor like this. This is actually a wire in this way, right? Imagine, and you rotate through this axis of rotation in this direction, and imagine that we have current applied to this wire. Or imagine this is the current in this direction. Make a loop, and we place this loop inside of a magnetic field. Right, this is a magnetic field. What happens? Well, in this case, we use we know that when we place a current, a wire inside of a magnetic field, a force is present, is acting right on the segment of the wire. And we found in the previous videos that that force is equals to current times L times V sine theta. Okay, now in this case, what should be that force? Well, this is the current, correct? We use the right-hand rule to find that force. If the current right here is going down, and the magnetic field goes in that direction, the force acting is in this direction, right? So we have a force, imagine, is coming out in this segment. What about this segment? It's gonna be the current going up, right? The magnetic field in that direction. Now the force goes into the wall. So what do we have? We have a torque in this way, correct? So we have then a rotation. The same thing as the example we did right before. We have a rotation. The same thing happens right here, right? We have a force acting in this direction, or a force on this segment, and that segment goes in that way. So we have then a rotation, correct? Perfect. Now, when you see this picture from above, you will see something like this. We have this extra rotation right here. This is a segment right here, correct? And we have a force acting in this direction. This is F1, this is F1, this is F2, and they were gonna be opposite, right? F2. Imagine for simplicity this distance is W and the length is L. Correct? Perfect. Now I remember that the distance gonna be W divided by 2. The same thing happened right here. It's similar one more time to the case when we have the force applied in this direction. We have R. Now R is gonna be 2W divided by 2. Remember the equation. The equation is torque is equals to Fr sine theta. Okay, the same thing as before. We have two forces in opposite direction. Correct. Now this is what clockwise. Oh, so this one is clockwise. It's gonna be, let's say, we can take a positive, right? Positive direction, just the direction itself. And then what do we have? We have torque tau is equals to what? Is equals to then the torque F1 times R. What is R? Omega divided by 2 times sine theta, plus, because they are in the same direction, plus F2, what else? Omega divided by 2 sine theta. What is the angle? Well, the angle is going to be 90 degrees, correct? The same thing right here, 90 degrees. Sine 90 is 1. But these two are the same. And then what do we have? This is twice. So it's equals to force times what? Times omega. Correct? Omega is this thickness. Now, but what is the force? What is the force equals to? The force is coming from this equation. And it's equals to what? The force is equals to then the force that is produced, all right, or the net torque, right? Now this is gonna be the gravitational magnetic force, correct? And we can get then the net torque. What should we get then the net torque? The net torque is equals to this force. What is this force? Is current L, right? V sine theta. That's force times omega. Correct? But omega or W times L, the length, give us the area. So this equals to what? This equals to current times area B, right, sine theta. And that's the torque acting on this loop. So torque tau is equals to current area B sine theta. Correct? Perfect. What happens if we have n loops? If we have n loops, well, we just multiply by n, right? That's the number of loops times the current times area V sine theta. Look, every time when we have in physics, when we have a vector and sine or a vector and cosine, we can represent this quantity as a product of two vectors. To do that, we can take the area now as a vector. Remember that a vector is a quantity expressed by magnitude and direction. In this case, this is the magnitude of the area, the product L and W, and the direction is going to be a line perpendicular to the surface, right? Let's say in this direction. Then we have this vector and we have this vector, and we multiply these two vectors. Correct? Perfect. We'll represent that in that way. Also, we can represent this quantity as a new quantity, because when we are dealing with a set of loops, right, when it's rotating, this quantity stays constant and this one also constant. Well, we make this product, right, is represented by B, actually by M, because B is the magnetic field, by M. M is the magnetic moment. This equals to numbers of loops, current times the area now as a vector, has magnitude and has the direction perpendicular to the surface. Right? This is the magnetic moment. Magnetic moment. So in this case, torque tau is equals to this magnetic moment. In case of vectors, well, this is for higher levels, okay, using calculus, but don't worry about it. Let's take it just like this. Torque is equals to magnetic moment times B times sine theta. Correct? Perfect. I can't believe it. So again, the magnetic moment is this product, represent this the area, numbers of loops and the current, and the direction is gonna be perpendicular to this surface, right, to the area. Got it? Okay, well, it's very important because thanks to this we have the electric motors, correct? We have current is connected or is placed, we have a loop with current placed inside of a magnetic field. And what do we have? We have the electric motor. Okay, that's the torque that is produced. This one or this one, right? Perfect. Now let's go to the next topic. The next topic is gonna be Ampere's law. Let's do it. Ampere's law. Ampere's law is similar to the Gauss's law or Gauss law. When we have the Gauss law, we found that the electric field times the area is proportional to the total charge enclosed by this area. For Ampere's law is similar to this one, but Ampere's is dealing with the magnetic field. So we have Ampere's law. The same thing, similarly to Gauss law, right? Imagine that we have current, right? This is current 1, current 2, and current 3. What should be the magnetic field created by this set of current? The same thing happens, right, for Gauss's law. We have different charges, Q1, right, Q2, and Q3. What should be the total electric field? Well, we use, right, a Gaussian surface to find the Gaussian surface. In this case is a sphere, imaginary sphere, and we can calculate in that way the total electric field. The same technique is used by ampere when we have current. But in this case, the magnetic field is produced in loops, right? Circular loops, closed loops, correct? Okay, and we take the same form. So now be the magnetic field times L, right? This is L, the total length of this loop, right, is proportional to the total current. Like in this case, this is the total charge, right, and this is the total current connected, right, or enclosed by this loop. Perfect. Let's eliminate this symbol using a constant. So B, the magnetic field, times L is equals to a constant. The constant is mu naught times the total current. From here we can solve for B is equals to mu naught, the total current divided by L, where mu naught is called the permeability of free space, okay, and the value is equals to 4 pi times 10 to the negative 7 Teslas meters per ampere. Okay, also L is the total length of the this loop at this circumference. So L is equals to 2 pi r, where r again is the radius of this loop. So in this case, what should be then the, according to Ampere's law, the magnetic field produced by this set of current? Well, it's gonna be mu naught times the total current divided by 2 pi r. We found already this equation before in the previous video, but again, it works. We get the same answer using Ampere's law and using the way that we used in the previous video. Correct? Perfect. Now let's go to the last topic. What happens when we have two wires and we're looking for the net force between two wires with current? Okay, let's do it. Imagine now that we have this wire, correct, with this current 1, and also this wire. These are parallel with current 2. What should be the, and again the direction is in the same direction, correct? What should be the force between these two wires? Okay, let's do it. Imagine that we take as a reference this wire 1, right? Or current 1. Well, we got current in this direction, so we have the magnetic field that produces, right? In this case, that's produced by this current, correct? And in this section, the magnetic field goes into the wall, right? And in this section is coming out from the wall, correct? Perfect. Now let's take this part. This is magnetic field produced by current 1. Let's take this one, right? Okay, let's use the same space right here. Now let's take this current and place it right here. Let's place this current, this wire right here. Okay, and don't worry about this part. Don't worry about this one now, for simplicity. Okay, let's do it this way. Okay, perfect. Remember we use the right-hand rule. We have current in this direction. And what else? We have the magnetic field in this direction. What should be then the force acting on this wire, on the wire? It's a wire, okay? Some wires. Well, we use the right-hand rule. We have the current in this direction, the magnetic field in that direction. So the force is going in this direction, right? We have the magnetic force, correct? And what is that magnitude? Well, we found it already. It's gonna be this one. So the magnetic force is equals to current 2, correct, times L Right, this is L has the same, they have the same length. For simplicity, L, what else? Times B, which B is the other one? B1 times sine theta. Perfect. But what should be B1? What should be B1 in this case? B1 we found, correct, from here. This is B, when we have a distance. Now this is the distance, let's say distance what? D, correct? Perfect. Now let's connect the other one right here. Now have this distance D, perfect. And then what do we have? Remember, the magnetic field at this point is at this distance D, and it's equals to what according to this equation? It's gonna be equals to, it's gonna be current 2L, what should be B1? It's gonna be mu naught. What is the current? Current 1, correct, times what? Or divided by 2 pi times D, correct, times sine theta. Perfect. And what is this? This is equals to current 1, current 2, mu naught, right? What else? L sine theta divided by 2 pi d. Or we can represent the force per unit length, right? We divided by L is equals to mu naught, current 1, current 2, what else? Sine theta divided by 2 pi d. Correct. The same thing happens for, we can do the same thing repeating. Let's find the magnetic field produced by this current is gonna be right in this direction, right like that. And we found that the current now goes, the force goes in that direction. So in this case, the two wires attract with this force per unit length, right? Force per unit length is coming in this way. What is the angle, one more time? What is the angle between? This is the angle again between the magnetic field and the current. Well, the angle is 90 degrees, right? 90 degrees. So we can say this is a force per unit length is equals to mu naught current 1, current 2 divided by 2 pi times d. The distance between these two wires or current. Correct? Perfect. And we finished this chapter with this analysis. See you in the next chapter. Thank you.